Chapter 6 focuses on building fraction foundations. Students will model fractions using area models, number lines, and set models. While learning fractions, a lot of misconceptions can occur. We will discuss the misconceptions in this video. In third grade, students learn how to write a fraction in fractional form, and that the top number in a fraction is the numerator, which is how many of the equal parts of the whole are being considered, and the bottom number is the denominator, the size of the fractional pieces being counted, and the number of copies it takes to create the whole. Next, students were introduced to the meaning of a fraction in a part-whole context in the form of area and length models. An area model is the area inside of a shape. A length model is a point on a line indicating a distance from zero. Students applied iterations, or the repeated placement of objects end to end, with unit fractions representing lengths on a number line. To find the length of 5/8, a student recognizes that the unit 1/8 of the whole is repeated 5 times. Now, let's move on to the new skills and concepts taught in this chapter. Students will begin by extending their knowledge of denominators to fifths, tenths, twelfths, and hundredths. It is important to note that although it is tempting to describe the denominator solely as the number of pieces a whole has been partitioned into, that is not always the case. For example, a slice of pie may be cut without partitioning the entire pie first. The slice is 1/6 of the whole pie, even though the pie doesn't have 6 equal parts. The next new concept students will learn will be a third type of part-whole model called a set model. A set model is part of a group. The other two models, area model and length model, are considered continuous models because they can be cut into as many equal parts as we wish. The set model is considered discrete because the quantities represent objects that cannot be divided further. Let's bring back the previous example of an area model and length model representing the fraction 1/4. Let's create a set model to represent 1/4 using circles and squares. There are a total of 4 pairs of shapes, and one pair of shapes is squares. 1/4 of the set is squares. The next concept students will build upon is fractions as measurement. The focus is on identifying an amount of continuous unit length, area, volume, time, and so on, and comparing that length to an amount equal to 1. The identified length can also be used as a measurement tool in determining the total length of an object. Students will use fractions when telling time. For example, 1 whole turn around the clock is 1 whole. 1/4 of a turn around the clock represents 1/4 of the whole clock, or 1/4 of an hour, also referred to as quarter past. There are a lot of misconceptions that may surface as students reason with whole number reasoning that does not apply to fractional application. Let's discuss some of these misconceptions. In whole number reasoning, a number represents a fixed count. For example, a 4 represents a quantity of 4 items, such as cakes. In fractional reasoning, the size of a fraction is determined by its relationship to the whole. 1/2 of a cake depends on which whole is being considered. Next, whole numbers can be compared by their magnitude. For example, 10 is greater than 6. However, in fractional reasoning, 1/10 is smaller than 1/6. Whole numbers can be placed on a number line in sequential order as 1, 2, 3, 4, and so on. When placing fractions on a number line, such as 1 whole, 1/2, 1/3, 1/4, and so on, they are not placed in sequential order from least to greatest according to the denominator. In fact, they are positioned on a number line in reverse order. Another misconception is that the numbers 3 and 4 are placed on a number line and are 1 space apart. When 3 and 4 are used in the fraction 3/4, this is now a number between 0 and 1. Next, whole numbers are compared using additive reasoning. For example, when comparing the difference between two whole numbers, such as 6 and 8, or 10 and 12, a student should state that the difference is 2. This reasoning does not work with fractions with different numerators and denominators, such as 6/8 and 10/12. It is incorrect to state that these fractions are the same size because both fractions are missing two pieces. In order to compare fractions, multiplicative or proportional reasoning is required. For example, additive reasoning states that 5 is to 6 as 10 is to 11. 1 is added to the first number to get the second number. Multiplicative reasoning states that 5 is to 6 as 10 is to 12. Multiply both 5 and 6 by the same factor of 2. Multiplicative reasoning began earlier this year when students began learning about multiplicative comparisons. Another misconception that students might have is viewing fractions as separate values when completing operations such as addition and subtraction. For example, 1/2 plus 4/2 is 5/4. The student added the numerator and denominator separately, when in fact 1/2 and 4/2 are both single values. The correct way would be to add the 1/2 size piece to the 4/2 size pieces to get 5 total half-size pieces. As students recognize fractions as single entities, whole number reasoning will apply to operations with fractions and to fraction comparisons. The next item to be on the lookout for is the idea that multiplication always makes the product bigger. This is true with whole numbers, but this is not the case with fractions. For example, 1/2 times 2/3 equals 2/6. 2/6 is smaller than both factors of 1/2 and 2/3. Finally, students have experienced whole numbers with one single numerical representation. For example, 7 represents 7 items. Fractional amounts, however, can be represented in other forms, as a fraction, 1/2, as a decimal, 5/10, or as a percent, 50%. Percents will not be introduced until 6th grade. This chapter lays the foundation of fraction understanding. Students will learn how to model fractions using set models, area models, and number lines. Students will also need to understand that a fraction represents one single value. The concrete and pictorial representation of fractions is key to developing fraction reasoning so that abstract thinking can be successful for the students. And remember, fractions can be a piece of cake.